Hello, everybody. Welcome to our talk. It's great to be here. It's great to have the opportunity to present our work in collaboration with SigOpt in the AI Summit. Today, my colleague Alex Lowden and myself, Shayan Mortazavi from Accenture Industrial Analytic Groups are going to present our work that we deployed a framework for monitoring the health of production critical machineries in industrial domain. There are a number of different maintenance strategies, but today's talk is going to specifically focus on predictive maintenance. The question we ask, why predictive maintenance? So at the time that IoT and the big data are increasingly being applied as part of the intelligent management systems, there are a number of studies and reports that suggest high value that can be gained by incorporating analytics into the maintenance domain. The savings, like the reduction in maintenance costs by up to 25%, reduction in asset downtime by 50%, and decreasing the scheduled repairs by up to 12% are all significant numbers for the asset operators to consider. So let's have a look at how maintenance strategies have evolved in time. As the complexity of the systems and processes have increased, there has been a shift in application of different maintenance strategies in the industry. So if the objective of maintenance is to increase reliability by maximizing the uptime and asset effectiveness, traditionally more reactive approaches have been applied. These approaches are simply letting the machines or systems to run to failure and then fix when broken, in effect. But following that, there were more systematic approaches developed called planned maintenance, which are scheduled maintenance activities driven based on the risk-based approaches, for example. In past decades, since 19th, a branch of maintenance has emerged called proactive maintenance, which is in effect based on condition-based monitoring systems with the objective of detecting anomalies and problems in systems early in advance in order to improve the performance. As a child of this preventative, proactive maintenance, predictive maintenance has emerged, which is in effect a fully analytics-driven approach that enables predicting and preventing the potential failures and issues before they occur. So there are these approaches allows optimization of maintenance in multiple different dimensions, cost, risk, and resources and supply chain. So in order to see whether all asset operators apply preventative maintenance or which of these strategies, we better have a view of what has been currently applied in the industry. So the tendency in the operation is to apply a hybrid of maintenance strategies based on the risk, based on the availability of the data, and the criticality of the system to the business. The tendency and trend that we see in the application of the predictive maintenance approaches is that they are mostly adopted for the critical machineries and critical systems sitting on the critical path of the production or a manufacturing plant. And this is mostly value-based sort of approach because they are often expensive and resource intensive. So what are these critical machineries? There are often likes of rotating machineries, high speed, like of turbines and compressors and pumps, heavy duty. They see multiple different operational regimes and modes, exposed to high operational loads, pressure, temperature. And because of their application, they are usually often modular design and with many parts and multiple failure modes for each part. Um, because these type of machineries sit on the critical path of the production or manufacturing line. If an unexpected failure happens, this often leads to a catastrophic consequences, sometimes leads to several weeks of unplanned shutdown. So, why these type of rotating machineries are good candidates for predictive maintenance? Because they are often, because of their complexity, are often equipped with hundreds or sometimes thousands of sensors, ranging from pressure and vibration, and flow rate, so on and so forth, monitoring the health of the asset at any given time and feeding the real-time data into integrated control systems or to the historians and recently in the cloud infrastructures. Because of the criticality of these sensors, they are maintained quite regularly and provide good reliability. So in the next part, my colleague Alex is going to talk you through some of the leverages and the features of predictive maintenance approaches.
Great, thank you, Shayan. So before we get into the framework that we've developed for machine learning and predictive maintenance, we wanted to talk to you a little bit about the types of problems that we typically see in predictive maintenance where machine learning can be applied. And this list is not exhaustive. This is based purely on our experience and what we see in industry. But what we typically see is four main problems where machine learning can be applied in predictive maintenance. So the first is the problem of equipment state or equipment health. So this is really looking at identifying the current state of a system or a component within a system and determining the health. So is this component in a healthy state or in a degrading state? So to give you an example, if you wanted to apply this type of feature, the equipment state on your car, then you may be interested to know if elements of the car, like the engine or the transmission system, were healthy or in a degrading state. Another common feature we see is time to event, which is taking that previous feature and sort of projecting forward. So this is looking at when you identify that equipment is in perhaps an unhealthy state, is projecting forwards or forecasting the actual remaining time until the equipment critically fails or no longer can perform its required function. The third element we typically see is root cause detection, and this is really guiding operators to the source of health issues. So if there is an issue, where is this issue occurring, and what's the likely mode of failure linked to the symptoms that you're seeing. And the final element is optimization, which is a combination of the previous three with considerations of resource and risk, effectively solving for the optimal time to intervene, to fix equipment, to repair equipment, etc. So for the content of this presentation, we're really going to talk to you about the first, the equipment state, and the third, the root cause detection. These make up the framework that we'll talk to you about today. So first, just to set the scene a little bit. So this particular project is focused on a greenfield asset, greenfield just meaning recently installed. And it's a processing facility, a hydrocarbon processing facility located in the UK North Sea. So this is an ocean between the UK and Norway. And this particular facility is a semi-submersible platform that sits in the middle of this ocean. Now, fluids, hydrocarbons, oil, water, they flow from reservoirs, oil and gas, they flow from reservoirs in the subsurface through wells to the seabed, and then through subsurface infrastructure called risers onto these platforms. Now, on these platforms, typically you have a number of heavy machineries, and typically you have a separation of the fluids, so separation into oil, water, and gas, and also pressurization for transportation to land. Now, the aim of the project is really twofold: to predict and prevent mechanical failures. And this has obviously sub benefits, the first being that you improve safety and integrity. So, by being able to predict and prevent these failures, you prevent these catastrophic events, which can have impacts in terms of safety and integrity. The second, on uptime, you can prevent or reduce unplanned downtime by predicting and preventing these events. You can also lower operating costs and reduce carbon emissions. So, in the event of an unplanned event due to a failure, often the hydrocarbon stream may be routed to the flare where it's combusted, which can result in increased carbon emissions. So, by solving the problem of detecting and preventing failures, you can also reduce your carbon emissions. So, really, what are the characteristics of building such a system to detect the health of equipment on such a green asset or a new asset? Now, there's really 5 characteristics to consider when building such a system. Now, the first is that any system you're building to detect the state of machinery, the health of machinery, and to guide operators to locations where there may be issues. The first is really the limited availability of historical failure data. So typically on these greenfield assets, where you only have 2-3 years of historical data, you have a limited supply of failure data. So the feed of labeled events is typically limited. On top of this, you have limited coverage of the multiple ways that machinery can fail. So for a given piece of machinery, there's obviously many ways in which it can reach a failure state or the point at which it can no longer function. And it's unlikely for these such greenfield assets that you have sufficient coverage of these failure modes to apply supervised learning techniques. So any framework that you're building to model machine state also needs to be able to leverage the large volume of sensor data generated by these heavy machineries. So these machines, like a gas export compressor package, which energizes gas, may have thousands of sensors across the machine, anywhere from millisecond frequency to minute level frequency. Such a framework also needs to be highly interpretable. So operators are going to be making decisions. An intervention in the North Sea could cost upwards of $500,000. And so any decisions or any insights provided by the tool need to come with a degree of interpretability to help the operators make those decisions. And the final element there is really scalability. So on these processing facilities, you typically have a lot of diverse machinery, so separators, compressors, pumps, each with a different function. And any method developed needs to be able to scale across these machines in order to provide you coverage of the asset. So all this together, all this considered, really necessitates the use of an unsupervised or semi-supervised approach for modeling the state of equipment on such greenfield assets. It's worth mentioning that common systems for this kind of problem exist, such as expert systems, where you have thresholds based on experience. These typically can be resource intensive to maintain and are not as scalable. So, what is this framework that we're proposing for monitoring the health of machinery and pointing operators to areas of defects? So, the framework really consists of 5 elements. So, the first element is building a projection for normal or nominal behavior. Once you have a projection for nominal or normal behavior, you can predict this forwards, predict this in real time, and then identify deviations from normal using what we're proposing here, a non-parametric dynamic thresholding, which my colleague Shayan will talk to you about. On top of this, we then propose layering in the mechanics of failure, the cause and effect relationships through a tool we developed called a fault matrix. Through this, insights can then be generated at a specific location within the machinery when defects occur, and it can guide the operator to then make a decision on how to remedy the situation. So on that first element, that modeling that nominal behavior, so how do you go about doing this? Well, these machines, these production critical machines like these compressors, typically contain thousands of sensors, and these might be vibrations, temperatures, and pressures. And these time series are often non-linear, non-stationary, with extended periods of unusable data. So perhaps you have two of these machines in parallel, or due to downtime, due to failures, you may also have large periods of unusable data. So you need to first, obviously, shortlist critical sensors within this full set. Now, by looking at the failure mechanisms and shortlisting a number of sensors, which still gives you sufficient coverage of those failure mechanisms, you can consider a subset of that full suite of sensors. Now, the use of LSTMs is particularly effective for modeling normal behavior on these sensors. So LSTMs, or long short-term memory neural networks, are, for those of you who don't know, just a specific architecture of neural network, a recurrent neural network, where you have information from computations passed between instances or between timestamps. Now, these LSTMs are particularly effective at modeling this normal behavior. And the way that they can be used in this situation is as a sequence to sequence mapping. So taking healthy data in and projecting healthy data out. Now, for individual sensors, like individual temperature sensors, which are indicative of certain failure modes, you may have a unidimensional to unidimensional mapping. But in the case where you have where health is relative to the movement of a group of sensors, then you can learn a multi-dimensional sequence to sequence mapping. So this then begs the question of, how do you train and maintain such a large number of LSTMs if you are using LSTMs to project normal for this critical subset of sensors? And so this is really one of the challenging and interesting parts of such a framework, is how to efficiently maintain and deploy this number of LSTMs. And this is where our partnership with SigOpt really came into its own. And there's a number of steps that we took in order to expedite this process. So the first is around really narrowing the architecture search space. So certain architectures of LSTM will lend themselves to certain sensor types, for example, vibrations or temperatures. You can also standardize your architecture to some extent by having, for example, masking layers, your first layer, to handle extended periods of unusable data, and then an LSTM layer and a dense layer, and then controlling capacity through number of neurons. We then reduce the requirement on resources by searching for hyperparameters with respect to multiple metrics, which is a nice feature you have available with SigOpt. So instead of just minimizing for validation loss, you're also minimizing for training time. So finding the best model that trains in the shortest amount of time. On top of this, performing distributed training with Bayesian optimization and parallelization on parameter search evaluation also significantly helps reduce requirement on resources. So each time you're evaluating a set of hyperparameters, you can be in parallel evaluating multiple suggestions simultaneously. And we found about a 10x resource saving compared to random search. So given this projection of normal, my colleague Shayan will now talk to you about the subsequent steps in the framework.
Thank you, Alex. So when we're considering an anomaly detection system to be robust, dealing with multiple different parameters that are measured with multiple different types of sensor, different noise characteristics and sampling rates. And also, on the other hand, as Alex mentioned, systems that experience and undergo multiple different changes in their state of operation and changes in the threshold and set points from the operation point of view, the anomaly detection has become a challenging task. So Alex talked about how we deployed LSTMs to handle the temporality and the change in the mood of the machinery operations. But in order to handle noise and uncertainty in the data, we employed a technique called nonparametric dynamic threshold. So this technique was originally developed by scientists in NASA, applied to the telemetry data received from the space shuttles. So why non-parametric? Because parametric assumptions are often susceptible to outliers and violated easily and result into a high rate of false alarms. And why non-parametric? Because these are a set of dynamically self-adjusting thresholds that move along the signal and understand the temporal effect of the signal. So how does it work? Basically, at any given time, these set of thresholds are applied not to the signal itself, but to an residual or error signal. And to detect an anomalous sequence in the error space, when a new set of observations are received, a wide range of possible threshold bands are evaluated, and the most optimal ones based on a criteria is selected. And that criteria is being which population of the outliers due to the threshold would result in the largest rate of change in the statistical properties of the error distribution. So once an anomalous sequence is detected, then this sequence is subject to calculation of a scoring mechanism, and the score is calculated based on the area of the sequence that sits outside of the threshold bands using the second moment of area. So far we have talked about a way that we calculate abnormalities and detect abnormalities and calculate the score for these abnormalities at sensor level. So how to make sense of these detected abnormalities from maintenance engineer point of view? To do that, we had to layer in and incorporate the domain knowledge into our workflow. So for that, we used cause and effect mapping, developed a specific technique called fault matrices that in effect is a method that links the sensors and the importance of the sensors to the modes of failure for each component. So how does it work? After receiving a set of observations, anomaly scores are calculated for all set of sensors, then fed into the fault matrices, and using this weighted importance matrix, then based on the failure modes of the components, something we call component anomaly score is calculated. So after this step, using the logics of reliability engineering, then these scores are ruled up and aggregated from component level into subsystem level, and by the same means from subsystem level to system level. This would give an overview, a bottom-up overview of the health of the system at any given time. Insights are generated based on the modes of failure for components and allows the end users to act on that. So the end users have the ability to reject or accept, and this is the step to close this loop and allow the user to provide their feedback. So in order to put everything into perspective, we are going to have a quick tour of the application that we have developed based on this framework. So what you see on the screen is an overview of the asset. In the main part, there is a process block diagram that shows the flow of the process, and the highlighted boxes are the active critical assets that are part of the model, and the green and red shows the are indicators of the health of the system. The left-hand side pane is the insights that are automatically generated, waiting for users to act on. So from this system overview level, we can drill down into a subsystem level where each system is broken down into major assemblies. In this case of a compressor, gas turbine, gearbox, and various parts of the compressors are comprising these assemblies, and a historical view of how abnormalities have been trending in time at subsystem level in order to get further diagnostics on what is going on inside each assembly. You can look at the components at component level, which components are forming this assembly. In this case, are a set of bearings and shafts and the internals of the compressor or pump. In the case of bearings, we see how historically the abnormalities have trended from a healthy to an unhealthy region. In order to deep dive and analyze what are the drivers, in the bottom we see all of the sensors that are driving these abnormalities. In this case, a bunch of bearing temperatures on the upper and lower bearings are indicating high anomaly scores. In order to allow the end user to investigate further what is the source of the deviation, then by clicking on the anomaly score, we see how the actual measurements are deviating from the predictions from the LSTM models, and how anomaly scores are increasingly indicating abnormalities. So once this anomaly scores are automatically resulting in generation of insights, then end users are able to take action and either accept or reject, and link their actions into the maintenance management systems. So this would provide an end-to-end overview of the tool that is based on the framework. I'll let my colleague Alex to wrap up and provide some of the learnings.
Great, thank you, Shayan. So just a final message here, but effectively since productionization, so this tool was productionized in 2018, numerous failure events have been correctly detected by the tool, and most importantly, 6 high-value events were identified and averted weeks before failure. So these are events that could have resulted in catastrophic consequences, and these were picked up by the tool a number of weeks before the failure. So we wanted to just finish with a couple of learnings. So 3 major learnings from the building of this framework. Now, the first really being around the fact that application of machine learning in maintenance requires embedding of domain knowledge to be successful. So we're really advocating this bottoms-up approach, combining with the mechanics of failure. The second is around the adoption of such a tool. Now, within the project team, we had a number of change management staff members who helped with the adoption of the tool. So such a tool obviously is new to the engineering workflow and requires significant cultural change. So this is not to be underestimated. And the third element there, just to finish on, is that the use of these digital accelerators like SigOpt is really critical for developing and maintaining such a tool. So really training a number like 200 LSTMs would not have been possible without such a tool. So on that note, thank you very much for your attention and your time.